In this video, we'll take a look at some of the basic calculus we need for this course. This video will be purely functional. Obviously, it isn't a substitute for a proper calculus course. It will just touch on one interpretation of the concepts of derivatives and integrals, and it will show how to calculate some elementary examples of each. Here, we see a function. This function is 1/2 x squared minus 3. I've drawn the graph of it over here. Now, what I'm going to do is I'm going to start drawing a bunch of tangent lines for this graph at different values of x. And we're going to illustrate what those tangent lines look like on this second graph over here. More specifically, we're going to map the pattern of the slopes of the tangent lines. Now, you'll remember that a tangent line is a line that passes through a particular point on the graph and which has the same slope as the graph at that particular point. So if I were to take this point, x is equal to -3, I could draw its tangent line something like this. So this over here that I've just drawn in blue is the tangent line corresponding to x is equal to -3. Now, if I were to take the slope of this tangent line, I could do it pretty easily. Let's see. The rise of this tangent line, or more correctly, its fall, it looks like it's about 3 units. And the run for this tangent line is 1 unit. So that means that this tangent line has a delta x, a change in x of 1 unit, and a change in y of -3, because at this point this line fell by -3 units. So the slope is -3 divided by 1, which is -3. Now what I'm going to do is I'm going to plot the pattern of the slopes on this graph over here. But to keep track of how they are changing, I'm going to write them out in a table over here. So the table will look like this. Here is x, and I will write out what is the slope of the tangent line at that value of x in the original function. So when x was equal to -3, the slope of the tangent line was also -3. And I'm now going to plot this value, -3, -3, on this graph down here. Now, I'm going to keep doing this for more and more points, but I won't make you sit through all of them. Now, let us see what would happen if we made a formal graph of all of these points that I plotted out. We get a straight line. So this straight line is a new graph that tells us what is the slope of the original function at any value of x. So for example, if I choose x equals 3, then this graph is going to tell me that the slope of the tangent line for this original function at x equals 3 is going to be 3. If I picked x equals 1.5, then this graph is going to tell me the slope at x equals 1.5. It's also equal to 1.5. And so on and so forth. So this second graph, which tells me what is the slope of the tangent line for every point along the original graph, is known as the derivative graph. And the symbol for the derivative graph is this. df dx. And as you probably noticed a pattern emerging over here, we can express this derivative graph as an equation. In this case, that equation is just x. In a moment, we will see how you can figure out what the equation is for any derivative graph, just knowing what the original equation was. I'm going to use this function to demonstrate how to solve for derivatives. Now, the adrenaline might be flowing through you at the moment, but I promise you it's really not very complicated to do. Again, I'm not going to go through all of the full details of what a derivative means or through the full derivation. All I'm going to do is just show you what the solutions are on a term-by-term basis. And fortunately, we can solve virtually every derivative question on a term-by-term basis. So here we see we have about 7 terms, so we just need to look at each term individually in order to figure out what the derivative is. So the rules are as follows. Rule number 1. If you see a pure number in the original function, that gets eliminated, zeroed out, when you take the derivative. And that kind of makes sense, because a synonym for a pure number is the constant term. And since a derivative is talking about a slope of a tangent line, or equivalently a rate of change of a function, the rate of change of a constant is 0. So we replace every constant with 0. Rule number 2. Whenever you see an x term, or any other case where you have a variable that has no visible exponent, that means it's raised to the first power. Anytime you see such a term in the original, you replace that with just the coefficient of that in the derivative. So here, the coefficient is -7. So we just need to replace what used to be the -7x term in the original with -7 in the derivative. Third, the next term is -4x squared. Now, we have a slightly more complicated rule whenever you run into a polynomial term like this. That is a term where the x is raised to a certain exponent. The rule is you take the exponent, multiply it by the coefficient, so that gives us -4 times 2x, and then reduce the coefficient by 1. So, -4 times 2, that gives us -8. X to the power of 2 minus 1 is just x. So the derivative of -4x squared is -8x. Of course, if you had a simpler function where you had just -4x squared, then the derivative would just be the -8x and you would just stop there. I'm showing what would happen if you had all of these added together. And what happens is that all of the derivative terms that correspond to each one of these gets added together as well. Let's keep going. The next term is sine of x. The derivative of sine is the cosine function. So a sine in the original turns into a cosine in the derivative. A cosine in the original, like this next term that we have here, a cosine in the original turns into a negative sign in the derivative. Next, an ln in the original turns into a 1 over x in the derivative. And last of all, any e to the x term in the original is maintained. It stays an e to the x. So now what we have done is we've gone term by term and we have figured out what each one of the derivatives for each one of these terms is, and that is the overall derivative for this original function. So here's a summary of all the rules. 1. The derivative of any constant term is 0. So any constant term in the original function gets eliminated, zeroed out in the derivative. 2. The derivative of a term that has a variable to the first power is just the coefficient of that term with no variable. 3. For polynomial terms, we find the derivative by multiplying the coefficient by the exponent and then decreasing the exponent by 1. 4. The derivative of sine of x is cosine of x. 5. The derivative of cosine of x is negative sine of x. 6. The derivative of ln of x is 1 over x. And 7. The derivative of e to the x is itself e to the x. There are a couple of special cases that we can come into, or some special patterns, which are going to help us whenever we need to solve derivatives. Supposing you run into a function like this. Now let's examine this function. This function contains something that we know how to take the derivative of, e to the x. The derivative of that is itself e to the x. But it's multiplied by this number out here, this coefficient. How do we take the derivative then? The answer is, whenever you have a function that's multiplied by the coefficient, all that happens is that the derivative gets multiplied by the same coefficient. So, for example, if you have e to the x, when you take its derivative, that stays e to the x, and the 2 which is multiplied on the outside gets multiplied in the derivative as well. So whenever you have a coefficient multiplied by a known function in the original, that coefficient just drops down unaltered into the derivative. Let's try a slightly more interesting example. Supposing I had f of x is equal to 6 multiplied by the cosine of x. Better still, let's make this negative 6 multiplied by the cosine of x. How do we find the derivative this time? Well, the derivative of cosine is negative sine and the negative 6 being a coefficient is going to drop down into the derivative. So we now have negative 6 multiplied by negative sine of x, which can be written more simply because the negative and the negative will cancel out as 6 sine x. The rule of constants
states that any time a function f of x is multiplied by a number c, the overall derivative is just that number times the derivative of the function.
Now, let's consider a different situation. Supposing you have a function like f of x is equal to the ln, the natural logarithm, of 3x squared. How do we solve for the derivative of this? The ln is easy enough to do, but we've only seen ln of x so far. We've never seen ln of something as complicated as 3x squared. Here's what we do in these circumstances. We take whatever is inside the parentheses, in this case 3x squared, and we find its derivative. Now, 3x squared is a polynomial term. So the way that we find its derivative is we take the exponent and we multiply that by the coefficient. And then we drop the exponent by 1. This is now the derivative of what was inside the parentheses. Then we have to multiply it by the derivative of what is outside the parentheses, but keeping what's inside the parentheses intact. So the derivative of ln is 1 over x. But in this case, we're not dealing with ln of x, we're dealing with ln of 3x squared. So that means that it's going to turn into the derivative 1 over 3x squared. The rule whenever you have a complex function like this, that is one function which is inside another function, is you take the derivative of the inside function and you multiply it by the derivative of the outside function, keeping the inside function intact. We can simplify this further. 2 times 3x to the 1, that can be written as 6x, divided by 3x squared, which then simplifies even further to just 2 over x. Again, the rule that we were following was take the derivative of what is inside the parentheses and then multiply it by the derivative of what is outside the parentheses, but with the inside intact. This process over here is known as the chain rule. Again, if you are taking calculus for the first time, this is going to be something you'll get a lot of practice with. So it's really just a preview of something which you're going to see in your Calculus 101 class. Let's try another example. Supposing we wanted to take the derivative of, let us say, the sine of 4x plus 3. The derivative of this is going to be take the derivative of whatever is inside the parentheses. So the 4x will become just a 4 because whenever you have just an x term, we take just the coefficient of that. The 3 is a constant term, so it turns into a 0. And then multiply it by the derivative of the thing that is outside the parentheses. The derivative of sine is cosine. And we keep the thing inside the parentheses intact. So that gives us 4 plus 0 is 4, multiplied by the cosine of 4x plus 3. And this is now the derivative of sine of 4x plus 3. 4 times the cosine of 4x plus 3. And these are both examples of the chain rule.
And the chain rule states that whenever you have a complex function, one function embedded in parentheses inside another function, you take the derivative of just the inside function, df over dx, and multiply it by the derivative of just the outside function keeping the inside one intact. That's symbolized as dg over df.
The opposite process of taking a derivative is known as taking an indefinite integral. An indefinite integral looks like this. We start with a particular expression that we want to find the antiderivative of. Then we write as follows. The symbol for an integral is this. Sort of an elongated S shape. And at the end, we write the variable that we're taking the antiderivative with respect to. So in this case, since the only variable present is x, I'm going to write dx at the end. And we are now going to take the antiderivative of this expression that is between the integral sign and the dx. Now, something that's important before we get started is we don't see anything above or below the integral sign. That's going to be important going forward. So, how do we do the antiderivative? Well, it's pretty straightforward, actually. All we have to do is to figure out on a term-by-term basis what expression or what function has this term as its derivative. Let's start with 3x squared. What expression has 3x squared as its derivative? Well, this is a polynomial function. So, whenever we were taking the derivative of a polynomial, we had to drop the exponent by 1. So when we're taking the antiderivative, we increase the exponent by 1. The other part to taking the derivative is that the old exponent or the higher exponent had to be multiplied by the original coefficient. So what coefficient must have this have had such that when 3 is multiplied by that coefficient, we end up with 3 in the derivative? The answer is the coefficient is 1. So we don't write anything. Now that means that x cubed is the antiderivative of 3x squared. Because if you were to take x cubed and you were to take its derivative, we get 3x squared. Now let us move on to the next term. Here we have an x. Again, this is a polynomial term as before. The only way that you can get an x is if you started with an x squared. Because if you took 2 and you dropped the power by 1, that would give you an x to the first power, which is what x is. Now, when you take the derivative, 2 needs to get multiplied by something in order to give you negative 7 over here. So what do you need to multiply that 2 by? The answer is negative 7 divided by 2, which is negative 3.5. So now, if I have negative 3.5 x squared, then when I take the derivative of this, I get 2 multiplied by negative 3.5, that gives me negative 7, and the power drops down by 1 from 2 to 1. So now I have successfully taken the antiderivative of negative 7x. I've found out what is the term such that when I take its derivative, I get negative 7x. And finally, the 0.5. The 0.5 is just a number sitting over here. But if ever you have a pure number, the only way you could have gotten that is if that pure number had been the coefficient of an x term. So that means that the antiderivative must have a 0.5x in it, such that when I take the derivative of this, I take just the coefficient and add it in. So this gives us the next term of our indefinite integral. We're almost finished. There's one extremely important step left, and that is whenever you have an indefinite integral, you always have to add a plus c to the end. No exceptions. If you don't add the plus c, it's wrong. What does the plus c mean? Well, remember that when we take a derivative, all of the constant terms, all of the pure numbers, get cancelled out? Well, when you do the antiderivative, you have to add them back in. So that's what that plus c stands for. It accounts for the fact that there was some constant term over here that had to be added back in. Now, there are going to be some questions out there where you're told what the constant value is. Another way to think of the constant value is, what is the value of the antiderivative when x is equal to 0? By the way that we symbolize an antiderivative is usually with a capital letter F, like this. So, whatever the value of f is when x is equal to 0, that is what the value of c is. So when we give our final answer, we would probably write it something like this. F of x is equal to x cubed minus 3.5 x squared plus 0.5x plus whatever the value of the function is when when x is equal to 0. And now we have solved the indefinite integral of this expression, or of this function. It is x cubed minus 3.5x squared plus 0.5x plus whatever value the function had when x was equal to 0. Let's try another example. What is the indefinite integral of the negative sign of 2x? So again, we need to find what function or what expression represents the antiderivative of this. What function is there out there such that when I take its derivative, I get negative sign of 2x? Well, the easy part of that is the negative sign, because the only function that gives you a negative sign is a cosine function. So we know that the answer has got to have a cosine in there somewhere. The 2x is also going to be perfectly fine, but now there's a problem. If I take the cosine of 2x and I take its derivative, then I'm going to have to apply the chain rule, because 2x is a more complex function than just x. If I wanted to take the derivative, this 2 would come to the outside, and the derivative of cosine of x would be negative 2 times the sine of 2x. There would be an additional factor of 2 here. So how do I prevent that additional factor of 2 from appearing? The answer is that the cosine has got to have a coefficient attached to it. Supposing I said 1/2 the cosine of 2x. In that case, when I take the derivative, the 2 is going to come to the outside, since that's the derivative of 2x. The derivative of half cosine is going to be half times negative sine. The 2x stays intact. And what's going to happen is that the 2 and the 1/2 will cancel each other out to produce no coefficient, or a coefficient of 1, which is precisely what we see here. Half times the cosine of 2x, therefore, is part of the antiderivative, and the full antiderivative is given by plus c. So this then is the antiderivative of negative sine of 2x, half the cosine of 2x plus c. The other type of antiderivative is an application known as the definite integral. Now, most of the calculation for a definite integral is very similar to that for an indefinite integral, but there is a tip-off for when you have to use definite and when you have to use indefinite. Here, I have asked us to find the antiderivative of 4x plus 3. But notice something. Now there are numbers above and below that integral sign. Those numbers mean something very specific. So we're going to work out how to solve this definite integral case. First things first, let's find out the antiderivative. What function, if I take its derivative, gives me 4x? Well, this is an x to the first power, which can only have arisen from an x to the second power. And since the exponent has to multiply by the coefficient whenever I take the derivative, that means that the initial coefficient must have been 2. Because if I multiply 2 by 2, I get 4. So the antiderivative of this first term is 2x squared. What about for the second term? Well, this is a 3, which is a pure number. And the only way that you ever get a pure number is if you take the derivative of a x term. Because a pure number only arises if you have that as the coefficient of an x term. If you're doing a definite integral, we stop here. We don't need to write the plus c at the end. Instead, what we do is like this. We write this whole expression inside square brackets, and then we write the 2 and the 6 outside the right square bracket. What does that mean? It means we're not done with our calculation yet. A definite integral is basically a way of working backwards from a derivative to the function that must have generated it, but we're evaluating that function at these two bounds, and we're finding the characteristic area which is associated with that function. We'll talk more about those areas in a later video. For our purposes, all you have to do is take this expression, evaluate it at the upper bound, so that'll give us 2 times, plug in 6 for x, 6 squared, plus 3 times, plug in 6 for x again, and then evaluate it at the lower bound, and then subtract the 2. So let's evaluate it at the lower bound. That gives us 2. Now we have 2 squared plus 3 times 2. Let's simplify this. 2 times 6 squared. 6 squared is 36. 2 times that is 72. Plus 3 times 6 is 18. Minus 2 squared is 4, times 2 is 8, plus 3 times 2 is 6. 72 plus 18, that comes to 90, minus 8 plus 6 is 14, and 90 minus 14 is going to give you 76. So the definite integral of this expression over here is solved by taking the antiderivative, evaluating it at the upper bound given to us by this integral sign here, evaluating it at the lower bound given by this number over here, and then subtracting the result at the lower bound from the result at the upper bound. That gives us, in this case, a value of 76.
To summarize, there are two types of integrals, indefinite and definite. In the indefinite case, the integral never has upper or lower bounds. We take the antiderivative of the expression between the integral sign and the dx. Remember, that means finding a function whose derivative is the expression between the integral sign and the dx. Then we must add the plus c to represent the undetermined constant. C is the value of the function when x equals 0. So if you're given that value, or if you can find it, then you can substitute that in for c. In the definite case, the integral has upper and lower bounds. We take the antiderivative as before, evaluate it at the upper bound, evaluate it at the lower bound, and then subtract the value at the lower bound from the value at the upper bound. This has been a brief summary of some of the results of calculus. We will see these applied in physics videos to come.